Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and this is lecture number 15 for chemical kinetics. Okay, in previous lectures I was discussing about the first order reaction and numericals related to first order. Now we'll go ahead with second order reaction. Integration rate law for second order reaction. We take common reaction, twice A gives products. Here concentration of reactant will be same. If there are two different reactants, we will consider the same concentration of A and B. Okay, here initial moles or initial concentration, let us say A, small a, concentration at equilibrium or at final concentration, we write A minus X, matlab X amount is used up. Okay, so we write differential rate law for second order reaction. Minus dx by dt is equal to A raised to X, where X is equal to 2. Okay, so we write minus dx by dt is equal to K A raised to X square, where this is concentration at equilibrium or final. So we write minus dx by dt is equal to K into A minus X whole square. Change the sides so that we write minus dx upon A minus X whole square is equal to K dt. Now integrating above equation, we get dx by A minus X whole square is equal to K integration of dt, and the answer is 1 upon A minus X is equal to Kt plus C, where C is integration constant. To find out the value of C, we have to consider initial conditions. So when t is equal to 0, this is initial condition, X will be 0, and therefore 1 upon A is equal to C. So this is the value of integration constant. Substitute this value C. So we will get 1 upon A minus X is equal to Kt plus 1 upon A. Okay, so we make the Kt as subject, so Kt is equal to 1 upon A minus X minus 1 upon A. If you simplify this, the answer will be K is equal to 1 upon T into bracket 1 upon A minus X minus 1 upon A. So K is equal to 1 upon AT into X upon A minus X, where A is equal to initial concentration of reactant A minus X will be concentration of reactant at time t, and X would be the concentration of reactant utilized at time t. Okay, so this way we know when at time t, so when concentration of both the reactants are equal, or if there is only one reactant but the order of reaction is 2, then we use this formula. This is integration rate law for second order. So above is the expression for rate constant of second order reaction, and here when two reactants are same. Okay, so the rate of reaction will be employed like this. Okay, now suppose two different reactants have total order of reaction 2, like A plus B gives products, and both have different initial concentration. For example, initial concentration of A, let us take small a and B small b. Okay, so in this case final concentration would be A minus X, B minus X, and this is dash. Okay, so now differential rate law is minus dx by dt is equal to K concentration of A raised to X, concentration of B raised to Y, where X is equal to 1, Y is equal to 1, so net order of reaction is 2. So minus dx by dt is equal to K A minus X into B minus X. Okay, change the sides. So we write minus dx upon A minus X B minus X is equal to K into dt. On integrating above equation, we will get K is equal to, this is the final equation, 2.303 upon T into A minus B log B into A minus X upon A into B minus X. This is the final integration relation for second order when both concentrations are different. Okay, so when A is not equal to B, we use this formula. Okay, so this is when A is not equal to B, we use this formula. When both concentrations are different, this is the case. Okay, now we'll go with next half-life period. For second order. So half-life period for second order. Here A is equal to B. So when A is equal to B, we use formula of K is equal to 1 upon AT X upon A minus X. Okay, or T is equal to 1 upon AK X upon A minus X, where so at T is equal to T half, matlab 50% reaction is over, X will be A by 2, that is 0.5 A. Okay, substitute these values and we will get T half is equal to 1 upon AK 0.5 A upon A minus 0.5 A. So this is equal to T half. T half is equal to 1 upon AK, or we can say T half is inversely proportional to 1 upon A. This relation is also obtained when A is equal to B. Okay, now we can use graphical method to express second order reaction. The first one is when A is equal to B. We use formula T is equal to 1 upon AK into X upon A minus X. Okay, so we use this formula. Now let us draw a graph. Let us draw a graph and here on y-axis we take X and on x-axis we take time t. Okay, here we can prepare two different sets to carry out these reactions. So the graph will be like this, where for this is for the set 1 and this may be for the set 2, where concentration will be half. Okay, now to find out our relations, we can take any concentration x. Okay, then for example this one. So with respect to this we have one t. So this is x1 and here we call it t1. Now half of this will be this one and we go ahead with this like this, and then we can have x2 and this is t2. Okay, so here the relation will be plot x against, this is x versus t in both the series and determine the time required to complete a convenient fraction of the reaction. Let the convenient fraction be y is equal to 10%. Then for set 1 we write a1 upon y is equal to x1, and for set 2 we write a2 upon y is equal to x2. Then we can say that x1 upon x2 is equal to t2 upon t1. Then it is second order reaction. So it's confirm the second order reaction when we get these conditions. Okay, so this is the way we can find out second order reaction with reference to graph. Okay, and we can draw one more graph for this one, which will be of one y-axis we take 1 upon a minus x versus t, and it will be a straight line for different sets. This is set 1 and this is set 2, and we can find out the slope a, b, c, and here l, m, n. Okay, so remember, for any set slope is equal to AB upon BC or LM upon MN, and which is equal to K. Okay, this is the graph for A is equal to B. But when A is not equal to B, we plot, then we use the formula K is equal to 2.303 upon T into A minus B log b into a minus x upon a into b minus x. Okay, and for that we draw a graph, this one, where this is log a minus x upon b minus x, and this is was time t. Then graph will be a straight line with slope, and slope is equal to AB upon BC. So K is equal to 2.303 into slope upon A minus B. Okay, this indicates second, straight line indicates second order reaction. So that's it in this lecture. Thank you so much.